So maybe we can talk about operators first today. Operators in quantum mechanics. So I'm going to just remind you that instead of having position as a function of time and momentum as a function of time, in quantum mechanics you have operator. And this operator doesn't depend on time, it's just an operator. So it's equivalent to multiplication by x. And momentum is another operator, minus I h bar d over dx. So, and these operators are fixed. Their goal is to act on what we call wave function. So then operator x applied to some function will be just multiplication by x. And operator p applied to wave function would be the derivatives. And in physics, it's very often when you replace derivatives over spatial coordinates with just prime. People lazy, they like shortcuts. So derivatives over time, you put some dots, and derivatives over x, you can put prime. If you don't like it, you can just keep writing d over dx. But primes will make a notation short and concise. So if you understand it, then there are two different ways to proceed. We can talk about operators themselves. What can you do about operators? You have other operators. You have energy, you have Hamiltonian, and actually you have more operators. So each operator may represent a physical quantity, like position, momentum, energy. This is also mechanical energy, the Hamiltonian, as a function of p and x. But it could be other operators like angular momentum, for example. Angular momentum as an operator. I have to move to 3D, r cross p. And other operators. And you can try to improve your skills and move forward in terms of operators. Another direction would be you talk about wave function. So you can solve for this wave function. It could be a Schrödinger equation as a stationary or non-stationary. So let's write stationary equation. Operator H acting on the state will be some energy. Or you can write a time-dependent equation. Operator of energy equals Hamiltonian applying to the wave function. So then last time we were trying to solve this stationary Schrödinger equation, yeah? Time independent. For infinite well square potential and finite square well potential. So you can move in direction of developing your skills and solving Schrödinger equation and analyzing solution. And you can also move in direction of the operators. And then you can calculate average values from operators over these functions. And you can find average position, average momentum, you can find average energy, and so on and so on and so on. And it's not easy to move in any of these two directions. It requires from you certain skills. And that's why quantum mechanics probably is not a very easy class. But it's not, yeah, go ahead.
Can I ask a question?
Yeah.
Can you clarify a bit what you mean moving on one direction or the other?
You can give, I'm going to talk about this right now, yeah, operators. I'm going to show you what you can do with operators. So one example could be, you can solve Schrödinger equations just using operators. For example, for harmonic motion. without any differential equations. Just knowing the property of x and p. Basically, these two operators is already enough to find a solution, a wave function, and energy for simple harmonic motion without even writing any differential equations.
Is that I don't want to distract you your scheme, but is that what is called a kind of a matrix approach for there are these two approaches, right? The Heisenberg is a matrix approach. There's
Not exactly, but you're right. In some sense, you develop, you can call algebra of these operators. So let's try to focus on the operators, at least for the first hour today.
okay.
So let's see what we can do just working with the operators.
Okay.
And there is something we can do. First of all, we can talk about eigenvectors and eigenvalues. So operators. So we can say, let's say you have an operator t. You can find such a state that when you act with this operator on the state, you're going to get the same function. Maybe some coefficient t. In this case, you would call this eigenvalue. Yeah. And the wave function, which corresponds to this eigenvalue, I'm going to put subscript label small t. This would be eigenfunction, eigenvector, or eigenstate. I probably call this eigenstate or eigenfunction. Function. What else can you do with operators? You can calculate average values. So an integral psi conjugated an operator like this. Yeah. I want to be more specific, so it is 1D over some function. Okay. Then if you calculate average value over eigenfunction from this operator, not any average value, but average over eigenfunction, then this operator can act, and you can replace this action by some constant, which is eigenvalue. So this constant, you can move it out, and then you have a integration wave function with itself. And if you have a normalized state, then this integral should be equal to just 1. So if you take an average from operator t over eigenfunctions, you can always get the eigenvalue. And actually uncertainty in value t would be 0 for eigenfunctions. But for arbitrary function, not necessarily eigenfunction, you're gonna get some value for this. And we have seen how it works for average position or average momentum and things like this. I want to make another step forward. I would like to do something else with the operators. For example, what if I would like to act with this operator not on the psi, but to the left, on psi conjugated? Can I act not in this direction, but in opposite direction? Is it possible? And you will see that this is a useful property if I can define action of my operator to the left, not to the right. Because normally operators act to the right, yeah, on wave functions. Can I try to do this? Well, in principle I can, yeah. And then if I can, this would be a definition of my Hermitian conjugate. So T cross, I'm gonna call Hermitian conjugate. It's like a complex conjugation in a sense, but because you're dealing not with numbers, you're dealing with operators, I'm gonna call this Hermitian conjugate for operator T. And it's defined as so if you have an integral with wave function on your left side, and let's say this is like psi 1, then you have operator T acting on psi 2, and I'm going to put a small brackets here, so meaning that my operator T can act to the right, and the space, the integration over space. If I can define the Hermitian conjugate, then it would be equivalent that you have a Hermitian conjugate operator acting on the state 1 on the left side. Complex conjugation multiplied by psi 2x. I'm going to just show that how the operator acts like this or like that. So you see, if you want to act to the right, then this is your operator T. But if you want to transfer the action to the left, on state psi 1 on the left hand side, then you replace it with T dagger. So Hermitian conjugate. If you can do this, then you can define what's called Hermitian conjugate, or you can perform Hermitian conjugation for operator T. Don't put too much behind it. It's just definition what we call Hermitian conjugation or Hermitian conjugate. So for example, just a couple of examples will be useful, I guess. Can I find Hermitian conjugation for operator X? I'll try to follow the definition and I can find X hat dagger. So then let me start from the left side. So the left side would be psi 1 conjugated, then operator X, psi 2, dx. So my multiplication, I multiply X with psi 2 right now. Can I move this X from psi 2 to psi 1? Is it possible for me? Can I write something like this? Would it be true or not? What are your ideas? It's true, yeah? My X is a real number, so I don't care about conjugation of X. And I can multiply X in any order. It's just 3 values. I can multiply them in any order. But if you think about it as an operator, this operator was applied to psi2, now this operator is applied to psi1. So let's look at the definition of Hermitian conjugate. What will be Hermitian conjugate for operator X? What is the conclusion? Can I claim that operator X dagger will be the same multiplication by X? Is it obvious or not? Can you confirm? Or it's not clear? What I'm trying to do, I'm trying to transfer the action of my operator from the right side wave function to the left side wave function. And whenever I can do this, I can call this Hermitian conjugate. And now I can see that my Hermitian conjugate is the same as my initial operator.
I think it's missing the sign right on the right side, on the x.
Sign?
Yeah, because you wrote the same operator, x and x on the left and right. Just
Yeah, the same operator, that's true. That means that my operator, if I calculate conjugate from this, is the same as my normal operator.
Yeah.
Yeah, this is the conclusion. So I can conclude that operator X will be equal to operator X dagger. It will be just multiplication by X. So I don't care in which direction I apply this operator, to the left or to the right. I'm going to get the same result. So operators for which Hermitian conjugate is the same as operator, that's called Hermitian operators. So X is Hermitian. What about linear momentum? Is it Hermitian operator or not? In reality, the question is tricky because operator is defined together with the functions it acts on. But I'm gonna show you like a simple version of this, like a light version of Hermitian conjugation for linear momentum. Find operator P dagger. What will be Hermitian conjugation of the linear momentum operator? Well, we can do the definition. Yeah, we can just try to write a normal action of my operator on psi2, and then I'll try to move this action from the right side wave function to the left side wave function. And if I can do this, then I can find Hermitian conjugate. And if I can find it, this will be the goal. In reality, there is a small trick behind it because it's not that obvious, but still. Let's try. The integration applied to psi1 conjugated x, operator P acting on psi2. I don't know if it's clear for you or not, but this would be this side. Yeah? Operator of linear momentum is acting on psi2. I hope it is clear. What I can do is this, I can just move minus IH bar out, psi1 conjugated, psi2 over x dx. How can I move this action to the left? Because I would like to end up with something acting on my left side wave function. So my right side wave function should be original. Is it a way for me to move these derivatives to the left or not?
Partial derivative?
Partial derivatives, do you mean integration by parts?
Yeah.
Integration by parts.
Yeah, integrate by part, yeah. My fault.
Let me remind you, u v prime dx. If I try to integrate by parts, I'm gonna get uv minus u prime v. Is it?
Yes.
Something like this, yeah?
Yes.
So then I can take derivatives and I can move it to the left. I have to pay price. What will be the price? Negative sign and surface term. So this is something I have to be careful with. So first of all, I'm gonna have a surface term. At minus and plus infinity. And then I can move derivatives, but I have to change sign. So I put plus instead of minus. That should be minus, yeah, from minus infinity to plus infinity. So I have a problem because I have surface term. I can't really present it this way because I have something extra, like my surface terms. Let's pay attention to the surface term. So if my psi1 and psi2 are arbitrary functions, then first of all, the integral, the average itself may not exist. But if my wave functions are not arbitrary functions, what should be the value for these functions at infinities? They should go to zero at large distances. How clear is this? Is it obvious? Otherwise, you can't integrate your wave function square. The function is not going to be normalized. It's not going to present physical states. This integral itself is not going to exist because you're integrated from minus to plus infinity. If your wave function doesn't go to zero at large distances, then the integral is not going to exist. So if I restrict my space for wave function and I just demand that my all wave function goes to zero at large distances, then I can get rid of surface terms. Don't trust me to the very end because it's not that simple. But let's just consider functions which are integrated when squared from minus to plus infinity. When functions are integrated, they must go to infinity at large distances. So then I can get rid of these surface terms. This is very important. Otherwise, I can never find Hermitian conjugate for my operator of linear momentum. Now, I'm almost done because look at this. I'm looking for some operator acting on psi1 and psi2 just untouched. It's original form. I have psi2 and I have some operator acting on psi1. So what I would like to present it is some operator which I'm going to call p dagger acting on psi1 and then psi2. Can you compare what will be my P conjugate if you just compare? Can you compare? What will be my P Hermitian conjugate?
We have that IH factor.
Mm-hmm. And then d over dx, yeah? I have a problem. Then it seems like P dagger is different from operator P. So this was my operator for linear momentum. Now we calculated P dagger, yeah? And you have this constant and d over dx. Does everyone agree that this IH bar will be just constant? Look, I put brackets here and I put conjugation. The correct answer is minus IH bar, because then an integral minus IH bar d psi 1 over dx and then conjugated,
Yeah.
multiplied by psi 2. So you see, when you take conjugation, minus IH bar will change to plus IH bar. Okay, yeah, it makes sense. So what will be the conclusion for me if I compare my P dagger and P? They're identical, yes? Can I say that my P dagger is the same as operator P? Yeah, I can say this. So operator P is Hermitian operator as much as operator X. They both are Hermitian operators. So when you have this matrix element, or when you have an integral psi 1 conjugated x operator P psi 2x dx, we can write it like this: the left side wave function operator and the right side wave function. So this operator P can act on any of these states. If I want, I can act to the right. It will be my operator P. And if I want, I can act with this operator to the left. This would be my P conjugate. But P conjugate is the same as operator P. So I don't really care in which direction I can act with Hermitian operators. If your operator is not Hermitian, then it's going to be difference when you act to the left or when you act to the right. Yeah. But for Hermitian operators, you don't care in which direction you act with your operators. So then I would like to make a claim and then study some properties of Hermitian operators. So Hermitian operators, the operators for which Hermitian conjugate coincide with the original operator. There's not going to be much of the difference. So properties of Hermitian operators. Hermitian So this means if you have operator T, when you calculate conjugation, it will be the same operator. So what kind of properties we can learn about these operators? Well, for example, let's find eigenvalues and eigenfunctions of this operator. Let's find eigenfunctions of t equals t dagger. So let's say my operator t is acting on some state. I'm gonna get some eigenvalue and the same function. Yeah. So we have a bunch of eigenvalues and corresponding eigenfunctions. For example, we can talk about Hamiltonian, and for each Hamiltonian you have stationary state and you have energy. So you have a bunch of solutions, and I would like to learn something about this, but the only restriction for me would be the operator itself is a Hermitian, so it's going to satisfy this condition. So let's consider matrix element between psi t1, my operator t, and psi t2. So when you have a left and right side different, you can call this matrix elements non-diagonal matrix elements. I'm going to calculate matrix element from my operator t over eigenfunctions, which corresponds to t1 and t2, possibly different eigenvalues. So let's say t1 is not equal to t2. Now, I would like to use the fact that my operator is Hermitian, and you can help me. Can I take my operator and act with this operator to the right? What I'm gonna get? If this operator is acting on the right, and this is eigen function. So tell me what I'm gonna get.
Do
T2,
times
yeah,
times the function
exactly.
against state.
Eigenfunction, eigenstate, doesn't matter. What if I try to act to the left?
T1. T1.
T1, yes.
Oh, I see. Yes, yes. It was covered here.
Maybe conjugate it. I'm gonna come back to this in a while, because if you remember the definition, when you act with this operator on psi1, you get eigenvalue, but this is under conjugation. So this eigenvalue will go out, but conjugated. So I want to be as accurate as I can, the maximum. Okay, second one. What if my T1 equals T2? So basically I just have a average over the same eigenfunction. I can rewrite this line, yes? But just gonna plug the same eigenvalues, and I can move eigenvalues out. So when I act to the right, I'm gonna get T psi T1, T2. And if I act to the left, I'm gonna get T conjugated psi T1. Actually, there is no T1, T2, sorry, there is just T, yeah? Just a one eigenfunction. So what can I conclude? For example, from the second line, can you say something about eigenfunctions or eigenvalues from the second line?
T equal to T conjugate.
Conjugated. So
Yeah.
because this is the same, yes, on the left and on the right side. And this coefficient cannot be zero. So this coefficient is just an integration of my psi t square. If it's a normalized state, most likely this would be just 1. And the same is here. So the one conclusion which I'm going to make is that t equals t star. What does it mean?
Real.
It's a real number, yes? Let's think about it. If you have Hermitian operator and you solve for eigenvalues and eigenfunctions, each eigenvalue must be a real number. You cannot get a complex number as eigenvalue for Hermitian operator. And this is nice, yes? Let me go back a little bit. If we are talking about operators like position, momentum, energy, angular momentum, each operator represents me some physical quantity. And eigenvalue for these operators, they represent possible value, like possible energy. For physical quantities, I would really like to have real values for energy, for position, for momentum. Yes, that would be natural. I can have a imaginary momentum or imaginary position or imaginary energy. So then if my operators Hermitian, like for example, position operator or linear momentum operator, then I can guarantee from the very beginning that my all values, eigenvalues, will be real numbers. This is nice. Then what can I say, what can I learn from the first line? I can move this constant out. And I can also take into account that eigenvalues are real numbers, so I don't have to put conjugation here. So from the first line, I can get T2, T1, T2 equal T1, psi T1, T2. And remember, this was the assumption that they are different. That was a different eigenfunctions corresponding to different eigenvalues. This was the same eigenfunction corresponding to the same eigenvalues. What can I learn from this? Can I cancel this? Because this is going to be in my notations psi t1 conjugated psi t2 and integration, yeah? And the same here. Can I just cancel this? What happens if I cancel?
T1 equal to T2?
But T1
Oh,
is,
yeah.
is not equal to T2.
Oh, yeah.
John's brother. John's brother.
So what? If I cancel this, I'm going to get T1 equal to T2, which is cannot be. What else can I say? how can I satisfy this equation? There's only one possibility for me. Can I move, let's say, the right side term to the left? I'm going to get something like T2 minus T1 multiplied by this matrix element. What does it mean? T1 is not equal to T2. I can just cancel this. That would mean that integration of my one eigenfunction with the second eigenfunction will give me
Yeah.
0. So in quantum mechanics, such integration is called scalar product or inner product or dot product. So integration of psi 1 x and psi 2 x dx I can write as a product of two vectors, like psi 1 dot product psi 2.
So they are like independent, like orthogonal.
Yeah, if I call this scalar product, so then for scalar product I would use my bracket notations. Psi t1, psi 1, yeah, psi 1. And dot product or scalar product or inner product with psi 2. I'm going to call this scalar product. And the scalar product of two eigenfunctions which corresponds to two different state eigenvalues is 0. I can formulate it as that state psi 1 is orthogonal to state 2. In a sense, they make angle 90 degree in some vector space. So we learn a lot. We learn that if you can find eigenfunctions and eigenvalues from my operator T, then we have a remarkable properties of eigenvalues and eigenfunctions. I can summarize it for you. So if operator T is Hermitian and all physical quantities corresponds to Hermitian operators. If my operator T is Hermitian and you solve the problem for eigenvalues and eigenfunctions for this operator, then you can conclude that T is real. So the possible values for this operator, you will never get a complex value for this. And the second conclusion, if you take your dot product or inner product or scalar product between these two eigenfunctions, you can get either, let's say, 1 if they're the same state, that would be just normalization, or you can get 0 if they're different states. There is something called degeneracy when one eigenvalue can have several eigenvectors. So, but in general, you can always pick eigenvalues and eigenfunctions which correspond to satisfy these conditions. And you can do this only for Hermitian operators, not for any other operators, only just for Hermitian operators. So then we can say, in quantum mechanics, we can postulate then if you have a physical quantity So you can put in correspondence operator, which is Hermitian operator. When you speak about Hermitian operator, it's defined relative to the scalar product. So this Hermitian conjugation is defined, I would call this relative to some scalar product or inner product. So whenever you have a space and you have a vector in your space, plus you're going to introduce scalar product between couple of vectors. So vector space and scalar product or inner product, it's something we call Hilbert space. Hilbert space. So then your wave functions, they exist in a Hilbert space. This means in addition to the wave function itself, you also have what's called scalar or inner product for these wave functions. Relative to this scalar product, you can define Hermitian conjugation and Hermitian conjugate operators, and physical quantities will correspond to Hermitian operators, which means that their eigenfunctions are orthogonal to each other and eigenvalues the real numbers. How do you like it? Isn't it good? Once I know this, I can make my life significantly easier, and I can prove a couple more theorems which will help you to understand further the algebra of operators in quantum mechanics. Because now I would probably say the most of my operators would be Hermitian, and I can rely on this property. There is one more property as well. Another property would be, so more. Once you have eigenfunctions of a Hermitian operator, they form a complete basis. In this Hilbert space. So what does it mean, complete basis?
You can express any other
Exactly.
things as a linear combination of.
If you have operator and you solve for eigenvalues and eigenfunctions, as a result you have a bunch of values and functions. These functions are orthogonal and normalized. Then you can say, if you have any arbitrary state, which is not eigenfunction or anything like this, but this function belongs to my Hilbert space. And remember, this Hilbert space is just a space of your wave function plus you introduce inner product for this Hilbert space. Can be expressed as a sum of eigenfunction for this operator T and some constant. So you look at this as a basis, and this would be coordinates. Remember how you break a vector into components. So this would be a component of vector psi, or maybe just function psi, and this would be my basis vector or state. So I can present any vector, any function, as a linear superposition of this basis. And these basis vectors or basis functions, they are orthogonal to each other, and they normalized. All you need to do is introduce a set of coefficients, which is the numbers. Instead of working with functions, you can work with a vector, a set of numbers. This is extremely important. And also I would like to show you how to make interpretation of this coefficient in just a second. But let's come back to the statement itself. I did not prove you that all this set of eigen functions, they form complete basis. This is something you can prove, but I'm going to skip it for this class. It's not that easy to prove. You have to really go deep into theory of vector spaces. Yeah, it goes a little bit beyond of this class. Just trust me on this. If your operator is not Hermitian, you can't really guarantee that you have a complete basis. One example which you may like. So let's say you have a vector space. They're like x and y, yeah? So then any vector in this space would be an arrow, like v. Yeah, this is my object, which belongs to my space. This is, think about it as a vector, a real vector in real space. Then how can you work with this vector? You can say, okay, let me introduce a basis. The unit vector in x direction and unit vector in y direction. So what do I know about these unit vectors? Well, I have to introduce a scalar product, so I can write something like this. Vector I equal to 1, yeah? That means it's unit vector. Vector j and vector j is 1. It means that this is also unit vector. And what will be the dot product between I and j?
0.
0. Which would mean that my vector I is orthogonal to vector j. Yeah? Then coming back, this is a basis. The basis is complete if I can take any vector v, and present it as a superposition of this x component and y component. So if you can find a vector for which you can't find vx and vy, then it's not complete basis. For example, if you think about x and y direction, but your vector is like this, yeah? So you're missing z component. Then x and y, it's not enough to describe this vector. So it's not complete basis. You need z vector. But if your vector is inside x and y plane, then this would be complete basis. So the statement on the previous page was that eigenfunctions of a Hermitian operator, they form a complete basis. That means any state you can present as a superposition of the eigenfunctions of this operator T. Okay, so let's say I can do this. It means that my basis is complete. How can you find Vx? I'm gonna apply scalar product or dot product, I'm going to say, okay, on my left side I put I, and on my right side I'm going to use vector V. So it will be a dot product between vector I and vector V. And because you have properties as linear for second argument, you can just say vector I, Vx, I, or maybe just, okay, I mix a little bit bracket notations and I and J, yeah, X plus Vy, J. What I'm gonna get? If you take a scalar dot product between the entire vector V and I, you're gonna get something like this, yeah? Vx, I and I, and Vy, Vx, I and J, yeah? What is dot product between I and I?
1.
1, I and J,
0.
0. So then you can find Vx then as you just taken a dot product between vector I and V. So let's look at the picture. This would be my Vx, yeah? You can take a dot product between vector V and vector I. It should be equal magnitude of the first vector, magnitude of the second vector, and cos of the angle here. V multiplied by cos theta, this is my Vx, yeah? It's supposed to be like this. So it's not a big deal. How can you find Vy, the y component? So my x component was a dot product V and I, and what will be the equation for the y component? What should I do?
J product.
J. And this is a good example because we kind of understand what's going on, yes? It's a very simple vector space. It's a two-dimensional vector space. We have a basis which is orthogonal and normalized, and we can present each vector into components. And this is how you can find components, like this. So coming back to our original task, I can look at this in the same style. I can say, this is my vector in a Hilbert space. So it's your vector V in a sense, yeah? I can present this vector V as a summation over some basis vectors. So these are going to be I or J or more. And I will have a component, some coefficient. So the meaning of this coefficient would be the component, yeah, Vx or Vy or so on. And you have a summation over all possible eigenvalues and some coefficients here. So I present my vector as a sum over these basis vectors with some coefficients. This is the same. The only difference is that my space has not 2 dimensions. My space may have infinite number of dimensions. how many eigenvectors I have. I can have infinite number of eigenfunctions. Remember this infinite square wave potential. We had infinite number of eigenfunctions. Also, my coefficients C can be complex numbers as well, not necessarily real numbers. This is the only difference, but this is the same. How can you find coefficient CT?
You multiply by each element of the base.
Finding CT.
Yeah, but this kind of normalized, right? So,
Yeah, for example, let me try to calculate dot product or inner product or scalar product between eigenfunction and my function. Something like this. Okay? So I'm gonna use this expansion. I'm gonna break this vector into components. I'm gonna use different label maybe. Lambda, C lambda, psi lambda, X. I'm gonna break this vector into components. So I have a summation. Then I can move these coefficients out. So the summation over lambda and coefficients will go out. And what will be the meaning of this? This is my dot product, yes? This is my inner product between eigenfunctions of the same operator. So then I can write it like this, summation over lambda, C lambda. Okay, we can do bracket notations, yeah? But this is what? They are orthogonal and normalized. That means when you have a summation over lambda, only lambda equal t will survive. If you have a different values for lambda than t, then this dot product would be 0. If you have the same value, then the dot product would be 1. So from all this summation, only one term will survive when lambda is equal t. So the conclusion would be that psi t dot product with my vector psi will be equal coefficient t. Let's compare this with the previous page. Look at this. The coefficient in the expansion can be found as an inner product between the basis vector and your actual vector. This is the same, yeah? The coefficient in the expansion can be found as an inner product between the basis vector and my vector. So it will help me to bring some interpretation for this coefficient. And this interpretation actually probably is the most important part of quantum mechanics. Maybe you will be rewarded from all of this calculation we just have done. So let's say you have a, for example, operator H. which is Hermitian operator. And we can find eigenvalues and eigenvectors for this operator. So I'm going to put some index n. So meaning that you have a set of eigenvalues and eigenfunctions. So what if your function is a superposition of two eigenstates? So where psi1, psi2, so they belong to this set of eigenfunctions. Eigenfunctions of Hamiltonian. Now I would like to focus on interpretation of this coefficient. How you can find the meaning of what do they mean, C1 and C2. Well, first I'm going to calculate a dot product psi and psi. So vector with itself. So you have an integration C1 psi1 plus C2 psi2 conjugated. It's my bra vector and multiplied by C1 psi1 plus C2 psi2. It's my ket vector. Yeah, it's a definition of this scalar product. To make notation more short, we can say something like this. We can introduce Hermitian conjugation to the vector. We can say you have a C1 psi1, C2 psi2 conjugated. This would be this part. And ket vector would be C1 psi1 plus C2 psi2. I wouldn't pay attention to this. It would be just exactly the same as this one. But when you take conjugation from Hermitian, from state, that just simply means you have to take a conjugation like under integration. So then my psi1 will be equal to bra vector. This will be on this side. C1, I have to make it conjugated, yeah? Plus the same for this one. This would be this part of my dot product and this part. So now I can open brackets. If you don't like bracket notations, if you don't like it, so you can just open brackets here. If you like bracket notations, you don't have to write integrals all the time. You can just open brackets here. It's just a language, how you're gonna write or manipulate it. But with time, you will find it more comfortable to switch to bracket notations because it's much faster than all your equations. Okay, never mind. Let's open the brackets. How many terms I'm gonna have when I open brackets? 4 terms, yes? C1, 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 C2, C2, C1, and C2 and C2. Let's work out each term. What will be C1 and C1? What kind of contribution I'm gonna get from this? C1 absolute value square, yes? C1 star C1. Then you have psi1 conjugated and psi1. Can I just write it like this? What else I'm gonna have? What will be C1 star C2? What kind of contribution I'm gonna have? C1 star C2. Can you help me?
Psi 1, yeah,
Psi1,
and Psi 2.
Psi1, Psi2. Okay, what else?
Plus C2, C1, C2 star,
Mhm.
Psi 2, Psi 1,
What else?
C2 square, and Psi 2, Psi 2.
So if you don't like bracket notation, you will have to write integrals all the time, yeah? It will be a little bit longer notations, but apparently you don't need bracket notations. You can just open brackets here and you will get the same. Done, the same answer. Now, let me recall that this was eigenfunctions, yes? And they are orthogonal and normalized. What is the dot product psi1 and psi1?
1, right?
1. Psi1 and psi2?
0,
Psi2 and psi1?
0,
And finally psi2 and psi2?
1.
1. So it will give me some conclusion that if you take a vector psi and would like to calculate the normalization of this vector psi, you're going to get c1 square plus c2 square. And in principle, I would like to put it to 1, yes? Because this is a normalization of my initial state. Very interesting. 1. The second, just to finish this, and if I want to make interpretation, I would like to calculate average from my energy from this over the state. I'm going to use the same notations, but in between, I'm going to put my operator. So for my bra vector, I'm going to have C1 star psi1 plus C2 star psi2. It's my bra vector. So operator H, the Hamiltonian, in between. And I can act with this H to the left or to the right because it's Hermitian, I don't care. So this is my operator. And then my ket vector. So now, if I open brackets, I'm gonna have 4 terms, similar like this one, yeah? What exactly I'm gonna get if I open brackets? Let me start. Psi1 square. You have to take bra vector psi1, then you have operator H, and then you have psi1, yeah? What else I'm gonna have? Let's say C1 and C2. What will be the contribution?
0.
C1 star C2, yeah, 0, but let's write it first. And then in between you have to put the operator, yeah? Between 1 and 2. Plus C1, C2 star, yeah? What will be the matrix element?
Psi 2, H, Psi 1,
And the last term?
C2 square, Psi 2, H, Psi 2.
So you see, the bracket notations, they help you to manipulate with such kind of matrix element in a much more elegant and concise way. So that's why I'm trying to move towards bracket notations. If it's too abstract for you, then you can always go back and have this integration. So basically this bracket notation, they represent me the integral over my space. I just don't want to write it. I just want to keep it this way. Okay. Now, if I want to calculate the average value, I have to first act with my operator on my wave function. And I don't care which direction to act, because it's Hermitian operator. I'm gonna act to the right. But this is eigen function, yes? Operator H acting on my psi1 will give me energy 1 and the same state. Operator H acting on psi2 will give me energy 2 and psi2. This is important for me. So then let's write it. This operator H acting on psi1 will give me what? E1 psi1, yeah? This operator H acting on psi2 give me what?
G2.
E2 psi2. Here, operator H acting on psi1.
Energy 1.
Energy 1,
Y1.
psi1. And finally, the last one.
Two.
But then, energy is a constant. I can move it out. And then if you move it out, you will have psi2 and psi2, yes? And then the result for this would be E2 multiplied by 1, because psi2 and psi2 is the same as here. What about this guy? You can move energy 1 out. You're going to have psi2
Yeah, but
and
that's 0.
at 0.
Yeah.
What about this guy, the first one? Energy 1 is out, and then you
One.
have psi1 and psi1.
Yeah, 1.
1.
Yes.
The final one, energy 2 is out,
Yeah. 0, 1.
and 0. Again, these terms, non-diagonal terms, will go away. Diagonal term will stay. So then my conclusion would be, if you take dot product psi and psi, you get something like this. And when you get average energy, you're gonna get something like this. So you can have energy, and my wave function, let me remind the wave function. My wave function is combination of two eigen functions, psi1 and psi2. How would you make interpretation of the coefficients now? Is it obvious? Because interpretation of them right now is on the surface. What will be the meaning of C1 square and C2 square? Look at this as an average energy. What should be the meaning of C1 square and C2 square? It should be probability, isn't it? Probability of what? Energy equal to E1, yes? What would be the meaning of C2 then? Probability of having energy equal
E2.
E2. So then let's call this W1 and W2. Then the first equation will look like W1 plus W2 equal to 1. Then the total probability that you can have either energy 1 or energy 2, the total probability should be equal to 1. The average energy would be probability to have energy 1 multiplied by energy 1 plus probability to have energy 2 multiplied by energy 2. So then what will be the meaning of this coefficient then? It's going to be amplitude of probability. So we can conclude with something cool. So C n, if you have more of them, is what? It's not probability, yes, you have to make it magnitude squared, so it's an amplitude of probability. Not to have certain energy, yes, but to find your system in state psi1, because state psi1 has certain energy. So Cn will be amplitude of probability for the system to be in the state n, psi n. This would be something to compare with this one. When you have a vector in normal space, yes, you have x component and y components. So your x component is a part of the vector along x direction, and your y component is a part of your vector along y direction. You don't make interpretations of these components more than this. In quantum mechanics, if you have expansion of your function over this over other states, let's say eigen states of an Hermitian operator, then the coefficients of this expansion will give you a chance or amplitude of probability that your particle, your system will be in this state or maybe in this state, yeah? So you have a different probabilities. And this is one of the important moments in quantum mechanics. It's called superposition. Superposition in quantum mechanics. So let's say my wave function is a superposition of two states with certain energy. Then then what kind of energy it has? It can have energy equal E1 because you can find your system in this state, but with some probability. And it can be in another state, yeah? It can have energy equal E2 with some probability, yeah? This probability C2 squared. Because the probability should satisfy normal equations, you can calculate, for example, normalization constant. So C1 squared plus C2 squared must be equal to 1. The total probability to find your system with energy 1 or 2 should be just 1. And you can find the average energy. Yeah. But the more important actually to think about the superposition from a more general point of view. Your particle, your state, does not have certain energy. Or it has energy 1 and energy 2 at the same time. This is a mixture of two states. So the particle may be in this state with some probability, or a particle can be in another state in some probability at the same time. I don't know if it's it should puzzle you, because it's a little bit counterintuitive. This is what makes quantum mechanics, the superposition principle. Particle may be in different states at the same time. So for example, let's say you have a couple of examples. Levels in hydrogen atom. State n equal 1, n equal 2, and n equal 3. So then let's say you have a psi1 eigenstate, psi2, and psi3. So my wave function may look like this, psi1. So what can you say about this state? Well, you can say that your electron is here, yes, on this level. You can say that the energy is E1. It's going to be pure state. You can say that your electron on this level, it has certain energy, and your wave function is very well defined. What if you say that your wave function of your electron is psi2? What will be the conclusion for you? Electron is on the second level, yes? These are going to be pure stationary states. But you can say something like this. Psi1 plus psi2 over square root of 2. How you can make interpretation of this state? What can you say? What is the energy in this state?
So it has half 1.5 possibility in psi 2 and 1.5 possibility in psi 1.
But this is not energy, it's a probability, yes?
Yeah, I mean unequal to state.
So you can conclude that the average energy would be
Yeah,
E1 plus E2.
over 2.
But this is average energy. What about energy itself? What is the energy in this state? The energy is not defined. The particle has no certain energy. With 50% chance, energy is E1. With 50% chance, energy is E2. Electron is on both levels at the same time. Electron is in both states at the same time with some probabilities. Let's have another example. Let's say you have a disk, not electron, disk. And you can spin disk like this. So I'm going to call the state up because the spin is up. And in this state, the z component of my spin would be, let's just say S. But you can also have a state when your disk is spinning in opposite direction. This way. So I'm gonna call the state down. And in this state, the z component of my spin, and basically I'm talking about angular momentum, is minus s. It's a macroscopic disk, yeah? It has certain state, let's say spinning, like this or like this. So what could be my wave function? Well, for example, my wave function could be just pure state up. In this case, my spin, sz, would be just s. My wave function could be pure state with the spin down. In this case, sz would be equal minus s. These are pure states. They correspond to different operators, different eigenfunctions, eigenstates related to the certain values of sz. But I can construct a function which is a superposition of spin up and spin down. So let's say I'm going to make it square root of 3 over 2 and 1 over 2. Yeah. In this case, it's 3 over 4, and this 1 over 4. The total normalization would be okay. Look at this. Look at this state. How would you make interpretation of this state? What is the spin of this particle or this disk if a wave function is like this? The spin is uncertain. Your disk at the same time is spinning this direction and at the same time is spinning in the opposite direction. Your state is a mixture of these two states. This is called quantum mechanical superposition. How do you like it? And before you make a measurement of the spin, there are both possibilities open. Before you actually touch it and try to measure the spin, you don't know what the result would be. You have a chance to get spin up and you have a chance to get spin down. And by the way, what is the probability to have spin up?
75%.
It was hard to hear you, Amar. 3 over 4, yeah?
75%.
Oh, 75%. What is the probability to have spin down? 25%, yeah? So you can calculate average spin. But average spin is not spin itself. So you have a 75% spin up and you have a 25% for spin down. So what would be the average? Is it S over 2? This is not that interesting. It's an average spin. What I'm trying to say that when you have just a superposition like this, it's a very, very counterintuitive. This is what makes quantum mechanics quantum mechanics. Your disk can spin in both directions at the same time. It can be in this state and in this state with some coefficients. And this is okay. This is what makes quantum mechanics so interesting. This is the same as electron can be in both states at the same time with different probabilities. Now, one more example. Let's say you have a, let's talk about quantum computers a little bit. Not seriously, yes, because quantum computers, it's a very complicated topic. Yeah? If you want to seriously discuss quantum computers. But versus normal computers, yeah? Classical computers. For classical computers, you store some information in memory, and you have these bits, yeah, bits. What can be the value in one bit? You can
0, 1,
0 or 1,
1.
yeah?
Yeah.
So then if you have, let's say, 1 byte, 8 bits, yes, 1 byte. Then you can put a number here. No, like 0, 0, 1, 0, 1, 0, 0, 1. So you can store some information. So then you have 1 byte for some integer numbers. Maybe you may want to have 2 bytes or 10 bytes or kilobytes or megabytes, or sometimes gigabytes or terabytes. But each 1 bit you can store either 0 or 1. And this is your classical computer. What about quantum computers? What if you take, instead of, and usually how you can just imagine this bit works, you put either, let's say, 0 volt, or if it's a capacitor, for example, or you can charge this capacitor and put some 5 volt, yeah, on a capacitor. So if capacitor has no charge, you would treat it as 0 volt, and if capacitor is charged, you would treat it as 1. So you can charge and discharge capacitor, and you can just, that means you can write numbers or you can delete numbers, and you can read numbers if you can measure the drop of potential. In quantum computers, your bit, quantum mechanical bit, can be in state which you make interpretation as a 0. Your quantum mechanical bit can be in the state which you make interpretation that it has 1. Let's say spin in one direction, spin in opposite direction, or charge, discharge, or whatever. But quantum bit or qubit, yeah, quantum bit, it can be in superposition of these 1 and 0 states. So what does it mean? If you compare to classical computer, your bit can be 0 or 1, yes? But in quantum mechanics, it can be 0 and 1 at the same time with different probabilities. So if you can implement such kind of bits, quantum bits or qubits, yeah, then the qubits will obey quantum mechanical rules. So they have the superposition principle. And if you can build a computer which can operate with qubits, so that means you can write something into qubits, and you can read something from qubits, and you can do some operations on them, yeah, like add numbers or subtract numbers, do something on these qubits. Then this is how you would construct a quantum computer which is going to work on principles of superposition of quantum mechanical states. And people wouldn't be so excited about it, but it was shown that there are problems in, for example, in cryptography, which you can solve with quantum computers much more efficient than with classical computers, like decoding some secret numbers. So then you can write an algorithm which will use this ability to be in superposition, and it will let you to solve a problem with a polynomial time. And for classical computers, the time was for solving the same problem will be exponential. And this makes a huge difference. So then people started to develop quantum computers as crazy, and then it's very interesting, and there are some technical problems and maybe even fundamental problems, like time of when your state will stay in this coherent state, for how long it's going to stay. And there are other things, but the idea of quantum computers is based on the superposition, on quantum superposition. I'm going to show you one more, maybe a couple more examples about superposition, but I'm just saying that it's very fascinating that your system can be at different states, meaning that you have a different values of some quantity at the same time. It could be about energy, it could be about spin, it could be about anything else. I don't even specify how you organize the qubits in quantum computer. One more example, which I believe is interesting to discuss, is the wave function itself, psi as a function of x. I would like to look at the wave function as a function of x with in different eyes, different approach. I would like to write something like this. My state can be presented as a superposition, and I'm going to pick eigenvalues of operators which have certain position. This state has certain position. Then if you have a psi equal to x, that means your very certain position, your distribution in space should look something like this. So the position is very certain. This would be my basis vector. But I'm going to have a coefficient. This would be amplitude of probability that your particle in this state. That's going to be amplitude of probability that you have certain position. And you have a summation over all possible states. This is the same as your vector v was a summation with this vi and some unit vector. Okay, let me write it maybe not as a sum, just like normal. Vxi, vyj, vzk. Yeah? I'm trying to say that when you talk about wave function, when you started to talk about wave function, I never wrote this equation before. Now I can say that my state can be presented as a superposition of states with certain position and the coefficient of proportionality. What is the coefficient of proportionality? Is the amplitude of probability for the system to be in the basis state, yes? Amplitude of probability. So amplitude of probability to be in the state x, meaning that have certain position. Meaning that be at point x. my wave function I worked before is amplitude of probability to find your particle at this point, at point x. So now I can write it in a more general form. I would say, okay, this was just my component. You have a state, quantum mechanical state, and you can pick a basis like this, and then my wave function, which I worked before, will be just a set of components. So what does it mean? It doesn't mean, it means that if you have this combination or superposition, you don't have certain position, your particle is at all these positions at the same time with different probabilities. Instead of having certain position, your particle is everywhere. Everywhere. But you have different probabilities. So you can be in state with x equal 1, or maybe with state with x equal 5, or maybe inside state when x equal minus 3. But you are everywhere at the same time. You have a superposition of the states. Your electron, if electron is described by this wave function, is everywhere with different chances. This is the same as here. Your quantum bit has two values at the same time with different probabilities. This is the same as for electron to be in different positions. This is the same as for this disk to spin in both directions at the same time with different probabilities. Or for electron to be at 2 levels or maybe at 3 levels, yes? So you can say, okay, maybe my wave function is a combination of 3. Why not, yeah? Then that means that your electron can be in all 3 states at the same time with different amplitude of probability. So this is what we call superposition. And this is what's hard to accept when you talk about quantum mechanics. So the last example, and maybe last for today, because I don't want to start solving Schrödinger equation for simple harmonic motion. I would say talking about superposition is already good enough. Yeah? It's a Schrödinger cat. Yeah? Schrödinger cat. Kind of a famous illustration for superposition because people could not really accept it easy. It's counterintuitive. How can you be in two different states at the same time? So when you bring this to level of atoms and electrons, probably you can say, okay, I don't have much experience with electrons or atoms, but can I bring this probability or superposition to the level of macroscopic objects? Like, I don't know. So you have a person in two different states, yeah? So can you form a wave function like this? When person is in normal state and upside down state at the same time with 50-50 chance. That would be an interesting, yeah, if you can do this. So quantum mechanics is not restricted only to microscopic objects. What if you try to write a wave function for a macroscopic objects and try to mix these two states. So then that was a funny questions arised immediately after quantum mechanics was created. And one of possible such kind of visually intriguing case or example would be, let's say you have a cat, yeah, Schrödinger cat. So now I have to draw a cat and I'm not sure how to draw the cat, yeah. Cat, yeah. And you have a poison. Poison. So, and you have a lock in this poison. So the state of this lock can be open. So that means your cat will die, yeah? If you open lock and poison will go out, the cat is gonna die. And your lock can be in a state closed. So then if poison doesn't go out, then the cat is alive. So then the joke is that what if you lock in a quantum mechanical state? What is a what if this is a microscopic lock? So you can apply quantum mechanics, and you can put this lock into a superposition between open and closed. Yeah? So then you have a probability that the cat is dead. And you have another probability that the cat is alive. But if you have a superposition, then it happens at the same time. Your cat should be dead and alive at the same time, because before you open the box and before you see the cat, you have a chance to get any of these results with different probabilities, yes? So this is what happens if you bring the superposition principle to macroscopic objects like cat. So there is something really non-trivial when you try to mix pure states and form this a superposition of them. But from others' point of view, this is the heart of quantum mechanics. This is how we derived quantum mechanics from the very beginning. Because from the very beginning, we were talking about probability to be at different points. We were talking about wave function, and we started to talk about interpretation of this wave function, how you make interpretation. That this is a probability or amplitude of probability for particles to be in different positions. So this was just a case of a more general principle, the superposition principle. So this is a logically consistent theory, the quantum mechanics. And the operators, because I want to come back to what we started from. When we were talking about operators and Hermitian operators, so the operators, they play actually a very important role in quantum mechanics. In particular, if you have operator which corresponds to physical quantity, you would like to make it Hermitian operators. So the eigenvalues, possible values for this value would be real numbers. Then you have eigenfunctions for this or eigenstates, which are gonna be orthogonal and forming a complete basis. And you can mix different states And this would be a superposition principle, like this. And this is how you can make interpretation of the coefficients when you mix different states. So there was last examples. I believe for today it should be enough. Maybe questions?